Hello, my name is Chase Harwell, and this is my final presentation for this course in hardware security and trusted circuit design. First, I'm going to talk a little bit about hardware Trojans, like what they are, and which ones were observed in the lab during this semester. What exactly are hardware Trojans? Hardware Trojans are malicious modifications made to the circuitry that makes up an integrated circuit chip. They can be implemented at any stage of the integrated circuit development cycle, but they are most commonly deployed during the design or the fabrication stages of the chip. Because of this, they can go undetected by both the designer and the end user if no tests are conducted on the final circuit, and the change that the Trojan makes is not easily observable. These Trojans can vary in attack functionality depending on the malicious intent of the attacker. The Trojans in this course could change the entire functionality of the original circuit, or in other words corrupt data that was output by the circuit, reduce the overall reliability of the circuit, or they could leak system secrets. In the case of the output being corrupted, the data would be useless to the original receiver since it is incorrect. Now let's go over the circuit designs that were observed during the lab section of this course. The first Trojan in Lab 1 was a Trojan that would leak sensitive information when it's triggered. The detection phrase of New Haven was used to activate the hardware Trojan. When the detection phrase was part of the input, New Haven would be replaced by the encryption key that the sender used to encrypt the message. The encryption key is very sensitive information, and if a program with malicious intent got a hold of it, they could decode encrypted messages sent by the victim and potentially put it at risk. In cases where sensitive information like credit card numbers or social security numbers are being sent in encrypted fashion, this type of Trojan could help attackers get access to that information. The second Trojan investigated in Lab 1 was a Trojan that significantly reduced the reliability of the original circuit. For this hardware Trojan, a key press of F12 on the keyboard that was connected to the FPGA would render the board locked. This means that no matter what was pressed or inputted, nothing would happen on the board. The only way to get the board to work again was to reprogram it. This type of hardware Trojan would have the greatest impact in cases where circuit reliability would be of the essence. These would be scenarios that involve like airplane autopilot systems or autonomous vehicles. Neither airplanes nor autonomous cars can afford to lose much functionality of their computer systems without there being potentially dangerous side effects. The third and final Trojan design that was investigated in Lab 1 was a Trojan that would completely change the output of the original circuit when triggered. This Trojan, like Trojan 1, had a trigger phrase as well. The trigger phrase for this Trojan was the word Moscow. Instead of leaking very sensitive information like Trojan 1, this Trojan would change the input phrase of Moscow to Boston before the encryption process occurred. This Trojan would likely have fewer ramifications than Trojan 1 because no secrets were necessarily revealed. A hardware Trojan of this type would have the greatest impact in settings where data accuracy is crucial. Next, let's talk about microarchitecture attacks and how they were observed in this class. What are microarchitecture attacks? They are side-channel attacks that will leak information from a victim process to an attacker. Unlike hardware Trojans, they do not directly influence the victim program or the circuitry that makes up the hardware. Instead, they reveal information by observing effects that the victim process may have on the already manufactured, Trojan-free hardware. There are many attacks in the real world today that pose serious threats to the security of our computing devices. Due to this situation, hardware designers have had to release security patches for already existing hardware and have had to keep these threats in mind when they are designing new hardware. Some of the most well-studied and well-documented microarchitecture attacks include Spectre, Meltdown, Rowhammer, Prime and Probe, and Flush and Reload attacks. The hardware attacks that have gained the most press are the Spectre and Meltdown attacks. Spectre is an attack that manipulates the processor into executing code that they should not be able to. This allows other processes to have access to the memory space of other processes, which may lead to sensitive information being leaked. Spectre attacks can be deployed on CPUs designed by Intel, AMD, Apple, and ARM. Meltdown attacks, however, can only be deployed on devices with Intel or Apple processors. The Meltdown attack takes advantage of a privilege escalation flaw in the processor that allows kernel memory to be accessed by a user process. Rowhammer is an attack that targets the main memory of a system. Studies have shown that most DDR3, DDR4, and DDR5 DIMMs are vulnerable to this attack. The Rowhammer attack will repeatedly open and close a row in DRAM in hopes to trigger a bit flip in another row that can lead to privilege escalation for the attacker process. The prime and probe attack will fill all cache lines of a cache set in hopes of a victim process also accessing the cache set at a later time. The attacker will then access all cache lines again and measure the access latency to determine if a victim process accessed the set. Finally, the flush and reload attack uses a shared page between the attacker and the victim to gain access to the data of the victim process. The attacker will repeatedly flush a shared cache line in hopes that the victim will reload it back into the cache. If the victim does reload the data, the attacker will then be allowed to hit on the data in the cache. Cache timing channel attacks are attacks that specifically exploit the timing difference between data accesses from the cache and accesses from the main memory. The difference in access latency between the two locations is obvious, as cache memory accesses are anywhere between 10 to 100 times faster than DRAM. Both the prime and probe and flush and reload attacks are cache timing channel attacks that observe these timing differences. Timing differences can also be noticed between different cache coherence states, as we saw in Lab 3. Mitigation of these attacks are difficult because of the performance overhead required for any of the current techniques we have today. The cache coherence protocol that was used in both Lab 2 and Lab 3 was the Messy Cache Coherence Protocol. This coherence protocol was used by some popular ARM Cortex-A9 processors, like the Apple A5 chip used in the iPhone 4S and the A5X chip that was used in the third generation iPad. In this protocol, cache lines can be put into one of 4 different states. In the modified state, a cache line is only present in one cache. The data is also marked as dirty everywhere else because the version in the modified core is the only truly correct version at this point. In the exclusive state, the cache line is once again only present in one cache. However, the data is still marked as clean because it hasn't been changed to a different value since it was retrieved from memory. In the shared state, the cache line may be stored in more than one of the system's caches. And finally, in the invalid state, the cache line is invalid or it's not present in the cache at all. In the second lab of this course, we used a prime and probe timing channel attack on a system that used the Messy Cache Coherence Protocol. This attack occurs in 3 phases. The first phase is a prime phase where the attacker fills all of the cache lines in a set with its own data. The next phase is the idle phase, where the attacker waits for the victim to place its own data in one of the cache lines of the designated set. Finally, in the probe phase, the attacker accesses all of the cache lines in the set and measures access latency to determine if the victim placed its data there or not. During the probing, one of 2 observations can be made for each cache line. The attacker could notice a low access latency. This would mean that none of the attacker's data was evicted and the victim did not place its data in the set at all. On the other hand, if a high access latency is observed for one of the cache lines, then it could be determined that the victim placed its own data there. The third lab used a similar prime and probe attack as Lab 2. In this lab, the Trojan process would put a shared cache block in a different cache coherent state to transmit secret bits. The 2 different states were the shared state, which meant that the Trojan wanted to transmit a 1, and the exclusive state, which meant that the Trojan wanted to transmit a 0. This type of timing channel attack is possible because the shared and exclusive states have access latencies that are ever so slightly different. During each iteration of the simulation, the attacker would analyze the latencies and then determine if the Trojan was trying to transmit a 1 or transmit a 0. In this course, there were different detection techniques that were used to detect hardware Trojans and timing channel attacks in the final lab. For hardware Trojans, detection would occur after the chip has been fabricated. Since the Trojans can be inserted during the fabrication process, it is difficult to test for any Trojans beforehand. Mitigation is also difficult since the Trojans would have changes made to the internal circuitry. One of the only good ways to mitigate the Trojan would be to bypass the piece of infected circuitry. In the lab, manual testing was done to determine the presence of a Trojan. First, expected outputs were recorded for a certain set of inputs. Then, manual testing of either the physical output that was shown by the LEDs on the board, or output clock signals were tested. For design A, my set of 16 different inputs only had 3 that would trigger all 6 of the Trojans, albeit with different outputs. And for design B, the expected output clock signal was found to be in the 5 kHz range. Every Trojan file was then tested to see if the Trojan was active. It was determined that if the output clock signal was in the 3 kHz range, then the Trojan was present. For cache timing channel attacks like prime and probe, detection would occur during simulations of a system with different processes running on each core. To detect if a prime and probe attack is happening, cache line ownership would be observed. If there seemed to be a pattern of one core owning all of the cache lines, then it might indicate that a prime and probe attack is underway. Trace A in the lab did show signs of a prime and probe attack. It could be seen in the second half of the 2000 run simulation that Core 2 alternates between owning all 8 cache lines in the designated set and only owning 7 out of the 8 cache lines. It was stated in the lab manual that the Trojan will use a cache line to transmit data to the attacker. Given this information, it can be inferred that Core 2 houses the spy process and Core 1 houses the Trojan process. It could then be concluded that a prime and probe attack is underway during most of the second half of this simulation. Trace B told an entirely different story than Trace A. There wasn't a single iteration in the run that one process owned all 8 cache lines in the set. Since the probe phase of a prime and probe attack fills all cache lines in a set, it could be concluded that Trace B does not show any signs of a prime and probe attack going on. In conclusion, hardware security is a field in the engineering realm that is always evolving. New exploits are always being discovered, so new detection and mitigation techniques must also be developed as well to keep user data safe from attackers. As someone who's interested in pursuing a career as an ASIC engineer, I thought it was really interesting to see all of the hardware Trojans that could be inserted into circuit designs and how they could be detected through rigorous testing. Overall, I thought this course was a great introduction to the topic of hardware security, and all of the labs provided me great experience using tools that I might need to use in my future career. Thanks for watching.